Hello, this video is going to cover Chapter 4 for our Introductory Chemistry class. This chapter is called Atoms and Elements. So we're going to start with the little pieces and then in our next chapter we'll move up to compounds and molecules. So we're kind of building on ourselves as we go through this. Now, one of the things that can make learning chemistry very tricky is that it's something that we can't see directly. And the graphic on here is a way to help illustrate that, but in all honesty, it doesn't make it any easier to grasp. So the graphic tells us that if we took all of the atoms in a dime and made them the size of basketballs, it would fill up the earth. Now, we're taking something or two things that we understand the size of, a dime and a basketball. But now we've managed to add in something that's too large to understand. So the trouble with understanding atoms or visualizing them is that they are so small that the amount of them is also inconceivable. So it's a very difficult thing to visualize or grasp because it's not quantities that we're used to seeing. So we like to use analogies to help explain them, to put them into sizes or numbers or terms that do make sense. About 91 of the elements that we have are found in nature, and it's weird to say that this is about. We would think that it might be something that should have a set value. The reason for that is because there's some elements that have been made synthetically in labs and then later have been found in nature. So there's some debate as to whether they are natural or not. And then there's about 20 more that have been made in the laboratories. And the elements themselves are unique. They each have a unique structure, which means they each have unique properties. And so we're going to talk about a little bit of history on how the atom was discovered, and then move into the periodic table and look at how that's divided and where we can find the different elements. So we're going way far back in history. We're going back to two philosophers here, and Leucippus is from the 5th century BC, and Democritus was around 460 to 370 BC. And these two guys were the ones that first said that matter is made up of small, indivisible particles, so small pieces that can't be broken up any further. What they really said was that if you take a piece of paper and you rip it in half, and then you rip it in half, and you rip it in half, and you rip it in half, and you keep on going, you'll eventually reach a piece that can't be broken down any further. And Democritus gave that a name. He called it an atom. So literally, an atom means indivisible or uncuttable. Now, this was a very long time ago, but the idea of the atom didn't stick. And there's a couple reasons for that. One, there wasn't any technology to back them up. And two, at that time, the person that got to send their ideas forward was whoever was the best at debating. And so just because these two were actually correct, whoever was the best at presenting their ideas and putting forth their argument was actually the one whose ideas made it through to the general public. So we're going to jump ahead 2,000 years to John Dalton. And John Dalton came up with the atomic theory in 1808. Now, these specific years, I don't care if you know them. I like to put them in there so we can see how much time has passed. We can see how close it is to recent time. But it's not a big deal to know exactly when it occurred. Dalton's atomic theory has 3 parts. The first part says that elements are composed of tiny, indestructible particles called atoms. So this is really the same things that the philosophers said. The second part says that all atoms of an element are identical. So that means that every carbon atom is the same as every other carbon atom. And a carbon atom is not the same as a sulfur atom. The physical properties and the chemical properties are what's going to make them identical. And the third part is that atoms combine in simple whole number ratios to form molecules of compounds. Now, they have to be whole numbers because we can't break them. So we know that water is H2O. We know it's a 2-to-1 ratio. It's not going to be one hydrogen to half of an oxygen. We can't break it into pieces. And they combine in simple ratios, and that's one of those words that depends on who's reading it and who's defining it. There are some molecules, especially if we look at large biomolecules, that have thousands of atoms, but that's the simplest form of that molecule. So take that word with a grain of salt. Today, we can see individual atoms, not with our naked eye, but with special equipment. So I'm linking us to a video here. So this is an incredible video still to this day. It's a few years old now, but it is literally showing.
We can look up at the sky and see.
So the video is incredible because it's literally moving one atom at a time, and it just shows how far our technology has come in order to create something like that so that we can see those individual atoms. So we're going a little bit back in time from that video. We're going to look at J.J. Thomson. And J.J. Thomson was around about the same time as John Dalton, a little bit later, but we have 1856 to 1940 for J.J. Thomson's birth and death years. So really not that long ago. And J.J. Thomson discovered the electron. And this was a really big deal because it told us that atoms have pieces. Now, up until this point, everybody thought that atoms were indestructible, meaning it just was a sphere, a solid sphere that didn't have pieces inside of it. And so this broke down John Dalton's atomic theory. It broke down what Democritus said. It's a brand new idea. And this electron that he discovered is very lightweight, and it has a negative charge. But this brought out more questions. Atoms aren't charged, so there has to be something that's balancing out this negative charge. So his theory that he came up with, his model, is called the Plum pudding model. And plum pudding's definitely a very British thing that probably none of us have ever had, so I like to use a watermelon to describe this. So on the left here we have his model, and we have our electrons that are very lightweight, and they're suspended in just a ball of energy. So that orange is just a ball of positive energy or positive charge. So in our watermelon version, the seeds are the electrons, And then the watermelon itself, the red, is all of the positive charge surrounding that negative charge. So it gives something to balance out that charge with. So J.J. Thomson asked his graduate student, Ernest Rutherford, to prove his plum pudding model correct. And in 1901, Ernest Rutherford did what's called the gold foil experiment. And to do the gold foil experiment, he shot alpha particles. So alpha particles were positively charged. He shot them at the gold foil. And if the plum pudding model is correct, the alpha particles should just go straight through an atom. So here's our picture, and I'm going to open up this video here in a second, but here's our source of the alpha particles right here, and they're going to shoot at this very, very thin piece of gold foil. I'm going to open this video so we can see what actually happened.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil. He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it. So, Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any. However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees. Based on his observations, Rutherford derived the following conclusions from his gold foil experiment. First, since most alpha particles passed through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point, as a small fraction of particles got deflected completely by 180 degrees, all positive charge and mass of gold atoms are present within a very small volume inside the atom.
So what our video tells us is that Rutherford was wrong, and Thomson was wrong, and Rutherford proved him wrong. And this gave way to the need for a new theory. And so plum pudding model is out, and we now have what's referred to as the nuclear theory of an atom. And it's called that because this is the introduction of the nucleus. So here is the nucleus right in the center of our atom, and the nucleus contains the protons and the neutrons. And this is almost all of the mass and the positive charge of our atom, and it's a very small volume. The electrons are in all of this empty space outside of the nucleus. So it's most of the volume of the atom and all of the negative charge and a very small mass. So they have this very opposite relationship. Our nucleus has a small volume and a large mass, and it's positively charged. The outside space has a large volume, a small mass, and has a negative charge. And in order for our atom to be neutral, the number of electrons has to be equal to the number of protons. So a little bit on the size of the atom, and this is based on It's based off of Dalton as well. But Dalton came up with a way to measure how much an atom weighs, to come up with its mass. And he originally based it on hydrogen and really just said that hydrogen weighs 1 atomic mass unit. So came up with a new unit. Measuring it with units that we are used to, like grams, gave a mass of 1.67 times 10 to the negative 24th. So that's a decimal place, 23 zeros, and then 167. Again, it's such a small value because they're so small in size that it didn't make sense. So coming up with a new unit to fit this new size made sense. Now, we still use the same idea of this, but we now base it off of carbon-12. So carbon-12 weighs exactly 12 AMUs, and everything else is just compared to that. A little bit more about charge. And this is probably stuff that you know or have seen before. But there's 2 types of charge. There is a positive charge and a negative charge. So on our slide here, the positive is represented with red and the negative is represented with yellow. And opposite charges attract. So we can see here that they're going towards each other. And like charges repel. So positive pushes away from positive, and negative pushes away from negative. And if we have equal amounts, 1 positive and 1 negative, we will end up with a neutral particle, a neutral atom or molecule. So here's our little summary table on our subatomic particles. We have our proton, our neutron, our electron. We have their mass in kilograms. We have their mass in AMUs, and we even just approximate these to say that a proton weighs 1, a neutron weighs 1, and an electron weighs 0. We have their charges, and then I'm going to add a couple extra pieces of information. We want to know their location. We know that the proton and the neutron are both in the nucleus, and the electron is in that empty space. And then the last thing I'm going to add over here is the symbol. So we see a couple different symbols for these. I'm going to write down the one that is the most common. So for a proton, it's a letter P with a positive sign, and an electron is an E with a negative sign. So it's the letter and then their charge, which makes sense, which means a neutron is an N, and because it's not charged, we put a little 0 there. So those are our most common symbols. Now there is a little graphic on here, a baseball and a rice, and the comparison is that if a proton were the size of a baseball, then an electron would be the size of a grain of rice. So again, we're using these analogies to help us understand something that is just incredibly small. So a couple little quick practice questions here, and we will do more of these during our Zoom time. But it says, what is the mass and charge of a particle with the following subatomic particles? So in that first example, we have 8 protons, 10 neutrons, and 10 electrons. So to figure out the mass, we're going to add up the protons and the neutrons. We don't need to include the electrons because they don't weigh enough to make a difference. So this particle would have a mass of 18 AMUs because they each weigh 1 AMU. For the charge, we're going to compare the number of electrons to the number of protons. And we can even write it out into an equation and say that the charge is equal to the protons minus the electrons. So for this, we're going to say 8 minus 10, and that will give us a -2. So we have a -2 charge. You can also look at it and do it more from a logical point of view. If we have 8 positives and 10 negatives, 8 of those negatives are getting canceled out, and so that leaves behind 2 negatives. So we would have a -2 charge. In the second one, we have 25 protons and 23 neutrons and 22 electrons. So if we use our same formulas here, 25 plus 23 means that we will have a mass of 48 AMUs. And if we combine or compare the protons to the electrons, this time we have more protons than we do electrons. So we're going to have a +3 charge. I'm going to fix that so it looks like an actual U. There we go. So we're going to move on to talking about the elements specifically. Each element has a unique number of protons, and we can see this on the periodic table. The number that is on the periodic table, it's usually at the top. Each periodic table is a little bit different though, but it's usually at the top. It is a whole number. This is called the atomic number, and it's abbreviated with a capital Z. I don't know why. It doesn't make sense to me either. The periodic table is arranged in order of atomic numbers. And this number is unique. So the 3 elements that are on here, we can see that fluorine has an atomic number of 9. That means that fluorine has 9 protons. It also means that any element that has 9 protons is a fluorine. If it has 10 protons, it's not fluorine, it's neon. So this is a number or a quantity that defines what the element is. And our elements can have 1 letter, like fluorine, or they can have 2 letters, like neon and helium. And if they do have 2 letters, then the first one will be capitalized and the second one will be lowercase. And it is important to write it that way, because if you write it with 2 capitals, then it will mean something different. So here's our a periodic table to look at for our next couple slides here. Some of the elements are going to be obvious. Carbon, nitrogen, and oxygen, they all are C, N, and O. It's 1 letter. It's the first letter of the word. Some are Latin-based. So potassium is K because the Latin name for it is calcium. And lead is Pb because the Latin name for lead is plumbum. Let me circle lead. And then some of them are named after people or places. So I'm going to circle a little row down here. So curium is named for Marie Curie, and Einsteinium is named for Albert Einstein. And berkelium and californium are both named for UC Berkeley because they were both created at the lab at UC Berkeley. Let me erase my circles down here. We'll do a little practice one. So we're going to fill in this table, the name, the symbol, and then the Z or the atomic number. So the first one on there is 10, and I'm going to switch colors. Actually, I don't think that'll show up. Here we go. So here is number 10. Let me move my video. So we can see that the symbol is Ne, the name is neon. We know that CO, we can find it right there, is cobalt, and we can see from our periodic table that its number is 27, so 27 protons, an atomic number of 27. And then the last one on the list is tungsten, and tungsten is right here. Tungsten is number 74 on the periodic table, and its symbol is a W. You should have a periodic table. If you have a hard copy of the book, then usually there will be one on the inside cover. If you have the soft cover of the book, then it doesn't have one on one of the covers. So I would find one within there and put a post-it note on it, find an online one and bookmark it. I always have one within arm's reach, so it's easily available. I'm not going to ever have you memorize names or symbols, which means that you should be able to find them and have them available in front of you. All right, so we're going to talk a little bit about history again here. And we're going to talk about Mendeleev. So Mendeleev was around between 1834 and 1907, and he's the one that first made the periodic table, and he did that in 1869. And he put the elements in order of their mass, which is not how we do it today. I just told you that it's done by atomic number. But at the time, there was only about 65 elements, and they were just in a list. So some people listed them alphabetically, some based off of how often they personally were using them in their lab or in calculations. And so because the discoveries were coming more rapidly, Mendeleev said that there needed to be a standard way to list them. And so he created the first periodic table. And he put them in order of their mass and then started to see patterns repeating. And so this has been called the periodic law. And what it says is that if we put elements in order of their mass, we will see properties repeat periodically. And so that means that each row or period, the rows are called periods, of our periodic table represents one cycle of these properties. So this is his first periodic table. It looks a lot different than what we see today, but the idea is that as he made his first row and he got down to the next element, he got beryllium, he put beryllium here, and then he made this list. He saw that lithium, sodium, potassium, rubidium, that they all were very similar. They reacted similarly, they had the same physical and chemical properties, and so he put them in a line. And he left blank spaces to be filled in later on by future scientists. And you can even see that there's some question marks in here because he assumed that there were elements that hadn't been discovered yet. And I think that this is one of the most incredible things because a lot of times scientific discoveries are put out and the person that's putting them out thinks that it's the end-all be-all. And so Mendeleev created this and allowed it to grow. So here's our modern periodic table. And the way that our periodic table is now is by atomic number, but it is still fashioned after what Mendeleev created. We've taken his and turned it on its side, but we do see those same patterns. So here's the elements I pointed out on that last one. Lithium, sodium, potassium, they are still all lined up together because they share very similar properties. So we're going to talk about some of the groupings on the periodic table, and these are based off of a couple different characteristics. So we're first are dividing our periodic table into three areas. We have a very large area of metals, and then a smaller area in that top right of nonmetals. And then we have this area right here in the center. So most periodic tables will have kind of a darker zigzagged line. I like to refer to it as the stairs. And our nonmetals are above the stairs, our metals are below the stairs, and then the elements that are right on the stairs we call metalloids. Scientists really like labels, and metalloids don't really fit into either grouping, so we just make them their own. So a little bit on each of these categories. Our metals are solids at room temperature. The exception to that is mercury. They're very shiny. They conduct heat and electricity. They're malleable, which means we can pound them flat, we can shape them into different things. They're ductile, which means that you can stretch them thin into wires. And the majority of the periodic table, 75% of the periodic table, are metals. Our nonmetals are, too many clicks. Our nonmetals are literally the opposite. They're found in all three states, so solid, liquid, gas. They don't conduct heat. They don't conduct electricity. They're very brittle in their solid form. and they're on the other side of the periodic table. Now there's one exception to that. Hydrogen is a nonmetal, but there are some periodic tables that will actually put hydrogen on the far right side because it is a nonmetal. And then here's our metalloids. Metalloids are also called semiconductors. They're also sometimes called semimetals, and they don't have one set of properties because they behave like metals and like nonmetals, depending on which one we're looking at. So silicon here is shiny and conducts electricity like a metal, but it doesn't conduct heat, and it's brittle like a nonmetal. So they have properties of both. All right, we're going to fill in a lot of information on this periodic table and then look at these different groups. Let me move my video. I think I'm just going to put my video right here in the middle because it'll be out of the way. So first, we're going to look at these big black arrows. I have one that says period. So the rows going across our periodic table are also called periods because they represent one period or one cycle of that repeating pattern. Going down a column, these are referred to as families or groups because the elements within that family share physical and chemical properties. So we're going to label some of these specific families and groups. And then I do have some areas that are labeled as A's and B's. So we have these two areas labeled as A. They're called the A group elements. They're also called the main group elements. And then we have this section here is labeled B, and over here is also B. These are the transition elements. And then these two rows, it's often can be confusing because it looks like it's its own periodic table. So I'm going to go back up to my periodic table here just to point out some numbers. Here we go. This is what I want. So notice the numbers here jump from 57 to 72, and down here 58 and 71, 89 to 104, 90 to 103. So these two rows, this is the 6th and 7th row of the periodic table, actually belong right here. And the only reason they're not put right there is because it wouldn't fit well on a piece of paper. So they get removed and put down as a little insert on the bottom of the page. So it's done for a really dumb reason, and it makes it more confusing. People don't always realize that it belongs in the middle of our periodic table. Because of where they're located, they're part of the entire transition metal family, but because they're kind of inserted inside of it, they are called the inner transition metals. All right, let me click back to where we were. Here we go. So these are also referred to as our inner transition metals or inner transition elements. All right, so I have a lot of colors there up at the top, and that's what we're going to use to label. So in our first column, our first group, these are the alkali metals. Notice that hydrogen is not included in that label. The next one over are the alkali earth metals. On the far right are the noble gases. And then the one next to that are the halogens. The entire middle section are our transition metals. And then the top row of the inner transition metals are called the lanthanides. And then the row underneath that are the actinides. So there are a handful of columns that we don't name. They do technically have names. They're not used as commonly though, because those families don't share as much in common. So if we just kind of look down one of these columns, we're going to have a mixture of nonmetals, metalloids, and then going into our metals. So those families aren't going to be as similar as opposed to our Noble gases over here, where they are all gases, they're all nonmetals, they're going to share more characteristics. So we're going to look at the 4 groupings and some of their characteristics that they share. So we're starting with the alkali metals. They are all metals. They're all soft metals. You can literally cut sodium with a butter knife. They have very low melting points and low densities. They burn pretty colors. So a lot of fireworks have these metals in them because when they burn, they give off reds and greens. They're very, very reactive. So the picture down here is sodium in water. Sodium reacts with water and when it does, it catches on fire. The alkali earth metals are the next column over. They're a little bit more what we'd expect from a metal. They're a little bit harder. They have a little bit higher melting points. They do still burn pretty colors. And they are reactive, but not as reactive as their neighbors. So it's kind of everything we saw in that past column, but a little bit toned down. And then on the other side of our periodic table, we have the halogens, which are all nonmetals. We have a little bit of mixture of phases though. Fluorine and chlorine are both gases. Bromine is a liquid, and iodine is a solid. They're all diatomic, which means they all come in pairs. So notice it's written as F2Cl2, and we'll talk more about that in our next chapter. They are also all very reactive. And then our last column are the noble gases. They are all gases, and they're very unreactive. So another way to say that is to say that they are inert. And that's where their name came from too. So they're noble gases. They're nobility. They don't need to interact with the other elements. So now that we've talked about what atoms are, we're going to kind of switch into how we can change the atom. And we can't change how many protons it has, but we can change the other 2 pieces. So we're going to start by talking about changing the number of electrons. And when we change the number of electrons, the atom will now have a charge. A particle with a charge is called an ion. So the term ion just means, just means that it's a charged particle. And I'm using the word particle to be very generic because it could be a group of atoms with a charge, or it could be a single atom with a charge. Our charge is the same as what we were looking at a couple slides ago, so the number of protons minus the number of electrons. When an ion has a positive charge, it's called a cation, and when it has a negative charge, it's called an anion. And this is Tommy Brown the cat here, and Tommy Brown is here to remind us that cations are positive because cats have paws. They're positive. And it's silly, but it will stick in your head because I think I learned that maybe when I was a freshman in high school, and I still remember that and I still use it. So in order to get a positive charge, our atoms have to lose electrons. And in order to get a negative charge, our atoms have to gain electrons. Metals are going to be the atoms that form our cations. So here's our sodium atom. When it's neutral, it has 11 protons and 11 electrons. And when it's charged, it now has 10 electrons, so it has that positive 1 charge. A calcium atom has 20 protons and 20 electrons when it is neutral. And a calcium ion will have 20 protons and 18 electrons. So because it has lost 2 electrons, it now has that positive 2 charge. And there's the same examples written out in more of a chemical reaction form. So let's look at the opposite. Let's look at the anions. Our nonmetals are going to form anions, and in order to do that, they have to gain electrons. So the example that's on here is fluorine. Fluorine is going to have 9 protons no matter what. And so when it's neutral, it has 9 electrons, and when it's a 1- charge, it will have 10 electrons. Phosphorus, when it is neutral, it has 15 electrons to balance out the 15 protons, and when it's a 3- charge, it will have 18 electrons, so 3 extra electrons. So when we write it out in a chemical reaction form, we're adding the electrons to our element, to our neutral atom, to get our charged ion. Now the periodic table can help us predict the charges that many of our atoms will have. These charges are not by random. These charges are very predictable. So this table is from your book, but what we can see are the charges that we know that these elements have. Now, it's not that the other elements that aren't labeled don't have charges, it's just that those charges can be different things. So the easiest way to remember it, +1, +2, +3, -3, -2, -1. So as we go across the periodic table, we're using that 1, 2, 3, 3, 2, 1 pattern, and it will be an easy way to memorize those charges. So we've changed the electrons. The other thing that we can change are the neutrons. An isotope is an atom that has a different number of neutrons. So it's not going to have a charge because adding or subtracting neutrons won't change the charge because they're neutral, but neutrons do have a mass. So it's going to change the mass number. And the mass number is going to be the number of protons plus the number of neutrons. So we have 2 symbols that we need to memorize right now. Our atomic number is abbreviated as a Z, and it's the number of protons. And the mass number is abbreviated as an A, and it is the number of protons plus the number of neutrons. The other piece of information that's on this slide is abundance, and so we can see that in an example over here for neon. It's showing us 3 different neon isotopes and what their abundance is, or if we looked at all the neon that's naturally occurring, 9.25% of it would be neon with a mass number of 22. That will come into play in a couple slides. We're going to have a little bit of math to do at the very end, and we'll use those numbers. So there are 2 different ways to write an isotope symbol. We can write it this way, where we have the atomic symbol in the center there. We have the mass number in the top left position and the atomic number in the bottom left position. And this is what would be the more proper way to write it, but because that can be difficult to type, we also see it written this way, where we are just using the mass number, because the atomic number is redundant. We know that if an element has 17 protons, it's chlorine. And if we know it's chlorine, we know it has 17 protons. So those 2 pieces of information are always going to be the same. So we're going to do one example here, and this is something that we will do more of in our Zoom time, but this is just kind of a quick little chart to kind of put all of that information together. So we have a complete symbol there for selenium, and we have 3 numbers on there. We have a 70, a 34, and a 3-, and essentially all of the information that symbol can give us. So our titles on our headline there are Z, the charge, A, number of protons, number of neutrons, and number of electrons. And there is going to be some redundancy here to emphasize that that number can represent more than one thing. So we're going to start just going down the line. So Z is going to be 34. And we know that Z is also referred to as the atomic number. We know the charge is a -3. That's on there. There's nothing to figure out there. And we know that A is 70. This is our mass number. The number of protons is 34. Z and the number of protons and the atomic number, all of those three words or phrases mean the same thing. The number of neutrons and the number of electrons take a little bit of work, but not a lot. We know that the mass number is the protons and the neutrons together. So if I just do 70 minus 34, then I will get to the number of neutrons of 36. And I know that my charge is a -3 and my protons are 34. So if I take my protons and subtract that charge, then I will get 37. I will get to my number of electrons. We know that the number of electrons has to be greater than the number of protons. So number of electrons is greater than the number of protons because we have a negative charge. So it's one of those things just to kind of check yourself to make sure that you've added the 3 on there instead of subtracting. All right, last topic in this chapter before I end my video is the atomic mass. So we've talked about the mass number. The mass number will always be a whole number. It's just the protons plus the neutrons. It's really a sum of all of the things that create the mass. But we also said that the mass of a proton and a neutron aren't exactly 1. So when we add up the atomic mass, this is going to give us the mass with a little bit more detail or precision. The atomic mass is what we find on the periodic table, and it's the number that is the average of all of the naturally occurring isotopes. So the number that's on our periodic table, I know this is very small. It's not important to see exactly what the numbers are, but on our periodic table, the numbers that are underneath will have some decimal places because they're representing an average of all of those isotopes. And we have a formula on our screen here. The atomic mass is equal to the fraction of isotope 1 times the mass of isotope 1, and then so on. And we have the little ... down there because it's telling us that this would continue on for however many isotopes there are. So I'm going to show you how to use this one time, and then again we'll practice it in Zoom as well. So here's our practice question. It says an element has 2 isotopes. Isotope number 1 has a mass of 84.9118 AMUs with a percentage, so this is our percent abundance, of 72.15%. Isotope number 2 has a mass of 86.9092 AMUs, and we're not given a percentage for that one. And the question says, calculate the atomic mass. Well, we know the formula. We saw that on our last slide. We know that our atomic mass is going to be the fraction of isotope 1 times its mass plus fraction of isotope 2 times its mass. So I have 3 out of those 4 variables to plug in. The one that I'm missing is the percentage for isotope number 2. This is very easy to figure out though. We know that our element only has 2 isotopes, so I can say 100 minus 72.15%, and I will get 27.85%. So we can always find that missing percentage. So now, to put this into our equation, I don't want my percentages to be in percentage form. I want them to be in decimal place form. So really what we're doing is we're just dividing those by 100. So I'm going to write this out as 0.7215 times 84.9118. So that's all my information for isotope 1. Plus 0.2785 times 86.9092. And then I'm going to plug those numbers into my calculator. I'm going to multiply, I'm going to add, and my calculator tells me 85.4680759. So just like with my other problems, I want to check to make sure things make sense. Here's our two masses that we started with. The atomic mass is an average of these, so my answer should be in between those. Now, it's not going to be perfectly in the middle unless your percentages are 50-50. It will be closer to whichever one has the greater percentage. So it's going to be closer to our isotope number 1 because it has the bigger percentage. Now, really, we're in between them. That's good enough for me. I know that I'm in the right ballpark. Number 2, we want to check our sig figs. Now, there's a lot of different types of math going on here, but really, we want to match our decimal places. So we're going out to that 4th decimal place. So I'm going to round my 0 up to a 1. So we're going to have 85.4681. And then the last thing, that third thing, is we want to add in our units. So we were in AMUs. Atomic masses are AMUs. So I'm going to tack that on the end there. And that is my atomic mass for my isotope. All right, that is it for Chapter 4. Thank you.